Two identical cylindrical tanks A and B are being filled with water. At a particular time, the water in tank A is 25 centimeters deep, and the depth of the water is increasing at a steady rate of 5 centimeters every 10 seconds. So here's the situation for tank A at a particular time. So let this time be the initial time for the process. An initial time is usually 0 seconds. Okay, and after 10 seconds, the depth will have risen by 5 centimeters. So the new depth will be 25 plus 5, which is 30 centimeters. Now this is a steady rate. The water doesn't just suddenly jump from 25 to 30 centimeters. So let's just look at the meaning of steady rate. Steady or constant rate. Okay, so we could use the word constant in place of the word steady here. So the steady rate of increase of depth is 5 centimeters in 10 seconds. Now we can break this down as much as we like. The interval doesn't have to be 10 seconds. We could consider 1 second. So we can also write this as 5 centimeters per 10 seconds. And if you write this by dividing 5 by 10, you get 0.5 centimeters in 1 second. Okay, the interval doesn't have to be 1 second. It could be any interval that we like, because we're dealing with a steady or constant rate. So for example, we could consider the rise of depth of the water after 5 seconds. So if I multiply above and below by 5 here, 5 ones are 5, 5 times 0.5 is 2.5 centimeters. So midway between 0 and 10 seconds is 5 seconds. So the depth of the water will be here, midway between 25 and 30. That's 25 plus 2.5, which is 27.5 centimeters. Okay, so the interval can be anything we like. It doesn't have to be 1 second. It could be 5 seconds, 10 seconds. It could be half a second. You know, suppose we want to find by how much the water level rises after half a second. 0.5 seconds. Well, we just get half of what's on top. Half of 0.5 is 0.25 centimeters. As long as this fraction works out to be 0.5. Okay, so the rate is 0.5 centimeters per second. 0.5 centimeters each second. So we can write it like this, /1 second. Well, we normally don't put in the 1. Okay, so we can take our time interval to be anything we like, not just these numbers here. At the same time, the water in tank B is 10 centimeters deep, and the depth of the water is increasing at a steady rate of 7.5 centimeters every 10 seconds. So we're referring to the initial time, of course. T equals 0 seconds. But now the steady rate is different. The steady rate of increase in depth of water in tank B is 7.5 centimeters per 10 seconds. If you want to break that down to 1 second, you can just divide above and below by 10. So that would be 0.75 centimeters per 1 second, which is, since we're dealing with a unit time here, we could write this as 0.75 centimeters per second. So anyway, I'll show the picture for the situation at t equals 10 seconds. So we have an increase of 7.5 centimeters. So this new depth will be 10 plus 7.5, which is 17.5 centimeters. Now, here we have a table showing the depth of water in each tank at 10-second intervals. So the initial time is 0, and we just add on increments of size 10. And we want to do this over 2 minutes. So we keep going till we get until 2 minutes are covered. Well, 2 minutes is 120 seconds. Tank A has an initial height or depth of 25 centimeters, as we know. And every 10 seconds that depth increases by 5 centimeters. So we just add 5 on repeatedly until we get to a final value of 85 centimeters at 2 minutes or 120 seconds. Similarly for tank B, the initial height or depth of water is 10 centimeters, and that increases by 7.5 centimeters every 10 seconds. So we just keep repeatedly adding 7.5 until we get to the value at 120 seconds. Each tank is a meter in height, and we want to find how long it takes to fill each tank. So 1 meter is 100 centimeters. So we can see that tank A is nearly full after 2 minutes. The depth of water is 85 centimeters, so we have another 15 centimeters to go. So after another 5 centimeters, after another 10 seconds, the depth of water will be 85 plus 5, which is 90, and we just extrapolate. Okay, so I'm extending the table here. 10 plus 120 is 130 seconds. The depth is going to be 90 centimeters. After another 10 seconds, the depth will be 95, and after yet another 10 seconds, the depth will be 95 plus 5 is 100 centimeters, which is 1 meter. So it takes 150 seconds for tank A to be filled, and the height is going to be 100 centimeters or 1 meter. Okay, we can convert this into minutes. We just divide by 60 seconds in a minute. So that's 2.5 minutes, or 2 minutes and 30 seconds. Now tank B is easy. We can see from the table that at 120 seconds or 2 minutes, the depth of water is 100 centimeters. Next, we will write down a formula which gives the depth of water in the tank at any given time. So let's call the depth of water in tank A D, and the constant term is going to be 25. That's the term that doesn't involve time. Okay, D is obviously some function of time. We plug in the time, predict our time, and we get the depth of water in tank A at that time. So we want the formula to be such that at t equals 0, the depth is 25. We're dealing with a steady rate here, so we're going to have some number multiplied by time. Okay, so we have to figure out what this number is. Well, this number is actually the rate that we saw earlier. Okay, but anyway, you can see straight away that if t is 0, then we have d is going to be 25 plus some number times 0. Well, that's just going to give us 25. Let's call this number c. Okay, you can work out what c is by looking at the situation at 10 seconds. At 10 seconds, the depth is 30. So if t equals 10, d is going to equal 25 plus this number c, which we want to find, times 10, and this has to give us a depth of 30 centimeters. So what is c going to be? So even if you don't know the rate, you can get it from this picture here, assuming that the rate is steady. Okay, if the rate is not steady, then d is not a linear function of t. It doesn't involve t to the power 1. It might involve something more complicated. So we're dealing with a steady rate, so d is a linear function of t. Anyway, you can see that well, what does c have to be? It has to be a half. Okay, 25 plus half of 10. That's 25 plus 5 gives us 30. And that's the rate that we saw earlier. You know, we saw that the rate at which the depth increases is a half of a centimeter per second. Okay, so that's two ways to think of this. Okay, so this is the rate, the steady rate, and we can also get it by just working it out, doing a little bit of algebra here. Find the depth when t is 10. We can find out what this number is. Just plug 10 in for t and just set this equal to 30 and solve. 10 times c is 5, so c is 5 divided by 10, which is a half. Right, we could also have used, you know, say t equals 150. T equals 150, the depth is 100. I could have put 150 in for t and set this thing here equal to 100 and solved, and we get the same answer of a half. Okay, let's do tank B. Well, at t equals 0, the depth is 10, so the constant term is going to be 10. Again, we're going to have some number times t, and that number is the rate. And we saw earlier that the rate is 7.5 centimeters per 10 seconds, but we want it per 1 second. Okay, so if we divide above and below by 10, we get 0.75 centimeters per 1 second per second. We can write this as 0.75 centimeters per second, so this is going to have to be 0.75. You can easily check this. If you put 0 in for t, you get 10, of course. If you let t equal 10, you get the depth in tank B equal to 10 plus 0.75 times 10. That's 10 plus 7.5, which is 17.5. So it does check out. Again, without knowing the rate, we could call this number something. Let's call it B, and say, let's look at the situation at t equals 10 seconds. Then the depth of the tank is going to be 10 plus B times 10, and we want that depth to be 17.5. And if you solve this equation, well, B times 10 is just 10B. 17.5 minus 10 is 7.5. So B is 7.5 divided by 10, which is 0.75. Alright. Okay, here we have a graph showing the depth of water in each tank over 2 minutes. So let's take tank A. Well, at t equals 0, the depth is 25, as we saw. At t equals 10, the depth is 30. So you could just pick those 2 points and draw your line. We're dealing with a steady rate, so the graph is a straight line. Okay, this is a linear function of time. It involves t to the power of 1, so its graph is a straight line. Also, the slope of the graph is the rate. This here is the slope, the coefficient of t. In general, a line has the form y equals mx plus c. The coefficient of the independent variable, that's the coefficient of x, is the slope. The independent variable here is not x, it's t. It's called t. The constant term is 25. That's the y-intercept, where the line cuts the y-axis. It's just written back to front here, but of course that doesn't matter. Okay, so instead of x we have t. For y we have the depth of the tank, whether we're talking about tank A or tank B. So if the slope is 0.5, it means that if we pick any point on this line, increase the independent variable t by 1 unit, 1 second, then y increases by 0.5 seconds. So that's the basic idea. Slope is rise over run, 0.5 over 1, which is 0.5. But of course we don't have to increase t by 1. We could increase it by any value. So if we increase t by 10, y will increase by 5, because 5 over 10 is 0.5. Okay, we're dealing with a positive slope here, so when we increase t by 10, we're going up to meet the line. Okay, we go up a distance 5. Okay, the second line is a little bit steeper. The slope is 0.75. It's greater than 0.5. So if we pick any point on the line and increase t by 1 second, we need to go up a distance 0.75 to meet the line. Okay, 0.75 over 1 gives us the slope. Again, we need to go up a distance because we're dealing with a positive slope. Next, we will use the graphs to find out how much time passes before the depth of water is the same in each tank. Okay, we can see from this that at t equals 60, the depth is the same, namely 55 centimeters. Okay, we can do that without the graph. So in the next part we're going to use formulas. We're going to use the formulas for the graphs. So we want the depths to be the same. Okay, so we want to find a value of t that gives the same value for each of these two depths. So we want to find a value of t that gives the same value for this expression as for this expression. So we put these expressions equal to each other because we want them to have the same value. Okay, so we've solved this to find the value of t that makes these two depths equal to each other. So if I bring the 0.5t over, 0.75 minus 0.5 is 0.25t, and subtract 10 from both sides. 25 minus 10 is 15. So 0.25t is 15. So to get 1t, we just multiply both sides by 4. 4 times 0.25 is 1. 4 times 15 is 60 seconds, as we saw in the graph. Now we can also see from the graph that at t equals 60, the depth is 55 centimeters. So, we can work that out using the formulas, of course. We could just plug this value of 60 seconds, say, back into this formula here, or the other one. We'll get the same answer. So if we do that, we get the depth of water in A is 25 plus 0.5 times a time of 60. So that's 25 plus 30, which is 55 centimeters.